right, so we're going to discuss colligative properties, which is a nice application of different solution concentration units. So I want to begin by reviewing some of these concentration units. Before I do that, however, I'd like to briefly introduce what a colligative property is, discuss the 4 known colligative properties, and give some mathematical relationships. We'll go over conceptual components of these colligative properties in more detail as we go along. So a colligative property is a physical property that depends solely on the concentration of particles. And really, it's independent on the nature of those particles. The particles can be molecules or atoms or ions. And there are 4 known colligative properties. There is the depression of vapor pressure, and this depression of vapor pressure is governed by Raoult's law. So if I have a beaker of pure, doubly deionized, doubly distilled water, and I begin adding particles to it, let's say I add NaCl. The more NaCl I add to the water solvent, the lower the resulting vapor pressure will be. The concentration unit that we use with this colligative property is the mole fraction. And the mole fraction is really a mole percent. If we have, well, in this case, let's say that we have 0.01 moles of Na plus 0.01 moles of Cl minus, and we have 0.9 moles of H2O. Of course, we should have more solvent than we have solute. Remember, the solute is the minority component. Whereas the solvent is the majority component. And so I have 0.1 moles of each particle. So let's go 0.2 moles of particles in a total of 1.1 mole of total substance. The mole fraction would be 0.18 for the ions, and it would be 0.82 for the solvent. The relevant formula here for Raoult's law is that the vapor pressure is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. And again, we'll talk conceptually about how this effect is realized by adding more particles to solution. Colligative property number 2 is the depression of freezing point. This brings us to a nice discussion of why in the South we salt roads after a snowstorm. And the reason isn't what most people think. It isn't to melt the ice, although this process is typically exothermic and does result in some melting. The real answer is that it forces Mother Nature to give a colder temperature in order for freezing to occur. So the relevant equation here is that the change in the freezing point is equal to minus I m kF. Let me explain a couple of terms here. I is the Van't Hoff factor. Van't Hoff was a very important early chemist, especially in the organic world, because Labelle and Van't Hoff proposed the tetrahedral geometry of sp3 hybridized carbon atoms. Here the Van't Hoff factor will allow us to predict into how many ions a particular molecule or formula unit may break up into. For example, NaCl has an idealized, not an actual, but an idealized Van't Hoff factor of 2, because you will produce an Na plus upon dissolution, and you will produce a Cl minus, 2 particles. Glucose, which is completely covalent and non-ionizable, has a Van't Hoff factor of 1. Also, the concentration unit is molality. Molality is defined as the moles of solute divided by the kilograms of solvent. It is temperature independent, and of course, temperature independence is precisely what we need in an experiment where the temperature is going to change. Now, this colligative property is very closely related to the elevation of boiling point. Before I begin discussing equations and concentration units and such, let's talk for a moment about what boiling point actually is. So we're going to do what Einstein would call a Gedanken experiment or thinking experiment. I'm going to take a beaker of pure water. And I'm going to take a larger beaker. I'm going to invert that beaker and place it over the smaller beaker such that I have a closed system. Water molecules at the surface interface of the liquid water and the air will have enough kinetic energy to undergo a phase change. So we will observe liquid water being converted to steam. And of course, we know from our discussion of gases that gases have much more entropy. They have free rotations, vibrations, translations. They will expand and explore the new freedom that they have, and there will be some instances where they collide with the container, in which you'll get condensation. They'll collide with the surface interface. Initially, there are going to be many more conversions from liquid to gas than there are from gas to liquid. But of course, this is going to be subject to chemical equilibrium, and eventually the rate of transforming a liquid water molecule to a gaseous water molecule is absolutely equal to the rate of transforming a gaseous water molecule to a liquid water molecule. At this point, every time I have an evaporation step, I have a condensation step. And the pressure that the gas molecules exert on the liquid interface is going to be constant. That gas pressure at that equilibrium is known as the vapor pressure. So vapor pressure is a constant for a given gas, for a given liquid, for a given molecule, and it is also dependent on the temperature. Obviously, the greater the temperature, the greater the vapor pressure. Vapor pressure is really a measurement of intermolecular forces. The greater the intermolecular forces, the lower the vapor pressure. Think of it this way. The molecules interact more strongly with one another, therefore not as many of them will have enough kinetic energy at the interface to go from the liquid phase to the gaseous phase. So we see that there's an inverse relationship between IMF and vapor pressure. Now, how is vapor pressure related to boiling point? Well, that's simple. The boiling point is equal to the temperature at which the vapor pressure is equal to the external pressure. So we've already seen the colligative property that when we add solute particles, the vapor pressure goes down. That means there is a concomitant increase of the boiling point. And with the boiling point, we will use molality as well. The elevation of boiling point is equal to the Van Hoff factor times molality times Kb. Now Kb, like Kf, are constants for a given substance at a given phase. So Kb will be a constant for liquid water that is in the process of evaporating. Kf is a constant for liquid water that is in the process of freezing. So notice the two experiments in which the temperature is going to change must use a concentration unit that is temperature independent. The fourth and final colligative property is the elevation of osmotic pressure. Now, the best way of describing osmotic pressure is, again, to do a thought experiment. So we're going to have a semi-permeable membrane in this U-tube. And we're going to have two solutions. I'm going to call the left side solution A. Solution A is going to be pure H2O. Right side is solution B. Solution B is a 0.1 molar solution of NaCl. We know that given a difference in concentration of solute or in solvent, that osmosis occurs by the movement of solvent from where the solvent is more concentrated to where the solvent is less concentrated. So there's two ways we can think about this. Solvent moves one from a high to a low solvent concentration, or from a low to a high solute concentration. Either of these is fine. They both mean the same thing. The important criteria is solute does not undergo osmosis. Water does undergo osmosis. It's the movement of solvent, not the movement of solute. There are some caveats to this. The DAT nor the PCAT will never capitalize on these caveats. So this is a generalization that we can all live with. So if I add more solute to B, so let's say I up the concentration to a 0.2 molar solution of NaCl, even more water is going to cross from chamber A to chamber B. Osmotic pressure is defined as the imaginary pressure that would be exerted by a square-headed piston that would prevent the net movement of solvent in any way, shape, or form. The relevant equation is actually a derivation of PV equals nRT. Pi, pressure, is equal to I M R T. In other words, PV equals nRT. P is N over V, which by the way is molarity, times RT. I throw in the Van Hoff factor to account for ionizations, and essentially osmotic pressure is PV equals nRT when I've solved for pressure. So two of these colligative properties will increase. Osmotic pressure will increase, boiling point will increase. Two of these colligative properties will decrease. Vapor pressure will decrease, and freezing point will decrease. So let's, one last thing we should discuss, and that simply is going to be, what is the conceptual understanding of this phenomenon? So let's take a look at that. If I begin to look at the vapor pressure, again, we're back to our beaker of water, and I'm going to illustrate a few of these water molecules, and I'm going to color code them. Where the hydrogens are yellow and the oxygens are red. And really what I want to emphasize is that the hydrogen bonds are between the hydrogens and the oxygens. These IMFs have to be broken in order for the kinetic energy of an individual water molecule to be sufficient for it to be translated from a liquid to a gas. Once I begin throwing in solute, not only do I have to break the IMF between the solvent molecules, I have to break them between solvent and solute. For example, Na plus will be surrounded by water molecules with respect to the oxygens, because the oxygens are partially negatively charged and the hydrogens are partially positively charged. So not only do I need to break the IMFs between the water molecules themselves, I have the additional burden of breaking them between the water molecules and the Na plus, or the water molecules in a different orientation when they are solvating Cl minus. So I'll just emphasize that right here. Now it's the hydrogens that are oriented to interact with the negatively charged Cl minus, and the oxygens are oriented away. Of course, I'm only drawing part of the picture here. So partial positive charge, partial positive charge, partial positive, partial positive. These IMFs have to be broken as well, which means at a given temperature, I'm going to lower the vapor pressure because there's more IMFs. Recall that vapor pressure is really the way we measure how significant IMFs are. The more significant they are, the lower the vapor pressure is going to be. And the lower the vapor pressure is, the higher the boiling point is going to be. So the molecular level explanation of half of our colligative properties is intermolecular forces. Let's look at freezing point for just a moment. The whole idea with freezing point is that the solvent molecules have to adopt a regular, repeatable, crystalline pattern before freezing can take place. So I'm using water as my example again. This will be a repeatable crystalline pattern. What happens in the presence of solute, and I'm going to cartoonishly represent my solute with an X, is that because I'm forming IMFs between solvent and solute, I do not get a repeatable crystalline pattern. It's much more random, the entropy is increased, and this depresses the freezing point. I have to slow the molecules down even more in order for this recognizable and repeatable crystalline pattern to be realized, and hence the solvent freezes. So IMF is really the core explanation as to why the colligative properties are the way that they are. Now, osmotic pressure is a little bit different. The whole driving force for osmotic pressure, for osmosis, is to reach an equilibrium between these two systems. So let's say that I have a 0 molar solution of NaCl, so it's pure water, and I have a 1 molar solution of NaCl. The whole point of osmosis is to have equal molarities on both sides of this semi-permeable membrane. So certainly the more particles that I have in the chamber with the higher solute concentration necessitates the more solvent that needs to cross, which necessitates the greater pressure that has to be exerted to prevent any movement of solvent. So these are some simple elementary explanations as to how colligative properties work on a conceptual level, how colligative properties work on a mathematical level, and in a future podcast, I will simply solve a bunch of colligative property problems for you.